السلام عليكم جميعا. واضح الصوت يمكم؟
وعليكم السلام. واضح دكتور؟
أستاذ واضح.
اوكي، في البداية نرحب بجميع حضور هذا الويبينار بخصوص موضوع Automation of Inflow Control Devices. طبعا في البداية انه فكرة هذا الويبينار كانت خلال زيارتنا إلى البوث الخاص في هذه الشركة في مؤتمر التكنولوجيا البحرية الأوفشور تكنولوجي كونفرنس اللي صار في مدينة هيوستن ولاية تكساس الأمريكية الشهر الماضي. كان لقائنا مستر برنت بروث وكانت بصراحة يعني interesting topic about the smart completion. So at the beginning we would like to thank Mr. Brent Booth and Mr. Saif Izzeddin for giving us the opportunity to present to the community, the SB community in Iraq, about these interesting topics. So at the beginning, I will give the mic to Shams Al-Huda that she's going to give a brief presentation about the topic.
السلام عليكم. أرحب بالجميع. I would like to welcome you all to today's webinar prepared by SBE Basra section with the Energy Research Center. Our webinar it's about automation and flow control technology and effective reservoir management solution in light oil environments to improve oil production. I'm Shams Al-Huda Sabah. I'm a student at Basra University of Oil and Gas in the third stage. The webinar today, it was about the first one of the major challenges and major oil fields and to improve recovery, developing and implementing new technologies that make operation efficient and cost effective. So as you know, for the reservoir with water gas drive mechanism, the mobility ratio between oil and water on gas becomes more critical due to the lower viscosity of water or gas. Once breakthrough occurs, gas or water production can rapidly dominate production, promoting well intervention or the shutting and of a production, leaving and recovered oil behind. For inflow control deceives and automation, inflow control deceives have shown oil production and recovery can be increased significantly with better inflow control pressure regulation along the lateral. However, neither of them are able to shut off unwanted gas and water production completely. The automation inflow control valve offers the functionality of conventionally and can actively shut off unwanted fluid completely. 6. The presentation describes the development of the automation and flow control valve as well as successful regional case students. So now I said the topic of a presentation, and now we welcome of the today's lectures. One, Brent Prof, Chief Commercial Officer. 2, presentation by Mahmoud Abdullah Fateh, Reservoir and Engineering Manager. So can you start with the Brent Prof?
Good afternoon, good evening, everyone. Thank you for the very kind introduction. My name is Brent Bruff. I'm the CCO for Inflow Control. I look after all of our subsurface reservoir and business development technical teams around the world. I'm based here in Abu Dhabi along with my colleague Saif, and Mahmoud Abdel Fattah is our reservoir engineering manager who's based in Saudi Arabia. Saif, would you like to say a few words before we begin?
Hi, good afternoon, everyone. My name is Saif. I'm the Business Development Manager for Inflow Control for the Eastern Hemisphere, based here in Abu Dhabi. Yeah, as Dr. Wathik said, there was a very good meeting between ourselves and himself at OTC in Houston, essentially looking to address the challenges that operators are facing in southern Iraq with the water and gas production. So what's going to happen is Brent will be introducing a background on the technology, on the company, and then Mahmoud Abdel Fattah will be addressing the details of the device itself and how we've been successful in addressing the operators' concerns here in the region. And then we'll finish up with regional case studies, proven case studies, and then we'll be addressing any questions you might have. Thank you.
Excellent, thanks, Saif. So yeah, let's jump right into this the presentation. So Saif, can you control, or do I have control? There we go. So I'm going to start by framing the discussion on why we're here and what our company is really about. You can see these two nice infographics here in terms of talking about, on the left, the unwanted gas that's flared. Not all gas is flared, we understand that, but a significant portion of the gas from oil reservoirs is flared because there's not a capability to handle or re-inject the gas. And notably, when you're producing the unwanted gas, that does a disservice to your goals as reservoir engineers to try to produce the oil and deplete the reservoir as efficiently and at low cost as possible. And on the right, you can see here the unwanted water. When you produce the unwanted water, it requires a lot of cost to lift the additional water, but also water doesn't generate any income when you're trying to produce the oil from the oil reservoirs. So when you look at these two key aspects, when you're trying to produce oil from an oil reservoir, the gas and the water create significant impacts to your ability to efficiently A, produce the oil, B, your cost to lift the oil, and C, your ability to deplete the reservoir in the most timely and cost-effective fashion. Next slide, please. Inflow Control is a Norwegian company, and our vision is to change the oil industry. And it sounds like a big feat, and it's not fluffy. Why we say that our vision is to change the oil industry is we believe from our core DNA that you can apply science and technology to help improve the way we produce the oil from the oil reservoirs. Full stop. And by doing that, that allows the operators to be more profitable, achieve their jobs with less risk in the operations, but it also adds a sustainability and cost benefit. Because when you produce less gas and less water and more net oil, you dramatically reduce the amount of emissions that come with each barrel of oil. And as we like to call it, it's just lower carbon oil, because we need to produce the oil from the oil reservoirs, but we need to improve how we're doing that. So that's our vision. Now our mission is how we're going to achieve that is by making better wells. So our focus is to work with the operators. You know your reservoir better than anyone else in the room, in the area, in the world. So we need to take your expertise, our technical know-how, and see if we can apply a technology approach to help you improve your net oil recovery. Next slide, please. So as I mentioned, we're a Norwegian-based technology company. And this is our headquarters, which is over 2,000 square meters. Hi. Sorry, was there a question?
No,
Sure.
no, go ahead.
Thank you. So when we're looking at the building, the entire building is owned by Inflow Control in terms of where we have our headquarters, reservoir engineering. We have our all in-house, made from bottoms up, full-scale flow loop capacities for our Aicbs. And when I say full-scale, to measure the joint in real applications. We don't have the ability to do dead oil. That's down the road at Equinor, formerly known as Statoil, which is the world's largest multi-phase flow facility, where we've done a significant amount of independent testing by a lot of oil companies. And why I mentioned this large research reservoir R&D facility owned by Equinor, Equinor has some of the best recovery factors in the world. So as an oil company, They have put a lot of investment into understanding how to recover oil and the longest duration of recovery factors at the most economical means. The three founders of Inflow Control all came from Statoil, now renamed Equinor. And their core DNA was what brought our vision and mission into Inflow Control, because they spent their life working at Statoil trying to understand how to improve oil recovery factors. So they spent an entire career working at the oil companies. And when they founded Inflow Control in 2011, they brought that ethos. And I also want to say it's an open door policy. If you have the ability to travel now that COVID restrictions have been lessened, we would love to host you. We have one of the best, if not the best, in-house labs that we do all of our testing, factory acceptance, multi-phase flow testing of every valve that we manufacture and produce. And we do everything in Norway on our valves. So we don't outsource anything into Asia. 100% is done and controlled by Inflow Control. And we do not let anything ship out of our facility unless it passes our very stringent QA/QC. Next slide, please. So we're going to talk about why we're here today, and that's to understand how we can minimize unwanted phases, such as unwanted water and unwanted gas. So in this cartoon, and we'll give you the links to the YouTube channel after the presentation's done, you can see where there's a green line across the top, and that's indicating an open hole or barefoot well that's drilled, as an example, into a carbonate. And the open holes, they do a good job for keeping the cost low. You drill it and then you produce the water, or produce the oil, pardon me. But when you actually have a breakthrough over time, the gas in the water has a much higher mobility ratio. And as you can see in the cartoon here, the gas migrates into the open hole. So what happens though is when the gas migrates into the open hole completion, then you have all of the oil left behind because the oil can't be produced because the gas overtakes the well. And then you have a stranded investment. So then you have unwanted gas being produced. You also have flaring potential, which comes up with CO2 emissions if you're able to actually handle the gas. In hundreds and hundreds of wells around the world, they don't have a means to handle the gas, and it becomes uneconomic. That means the wells get shut in, leaving behind a significantly valuable resource that could be produced. And we have a solution to do that today. Next slide, please. So a brief overview on the history of inflow control technology. This goes back 30 years. So our Aicv, this is the newest generation of autonomous inflow control valves. It was invented in 2011, the foundation of the company. But if we back up and go for a history walk in the past, Aicds or passive Aicds are essentially tools that distribute and delay the drawdown, but they can't stop the water or the gas. So they do a good job at delaying and deferring how the water comes up from below or how the gas may break through at the top, but it's coming regardless. So from the 90s to the 2000s, Aicds did a huge benefit for the oil and gas industry by helping defer or delay the water breakthrough and gas breakthrough. But in the early 2000s, Statoil, they said they're not doing good enough. We need something that's closer to an intelligent completion valve or a smart valve, such as a hydraulically controlled valve that you would install. But we don't want to run all the control lines to surface. They don't give us enough zones of spatial contribution, because typically the smart wells only have 3 or 4 zones, which means you still, if you shut off that zone, you leave a significant amount of oil behind. And we're here to improve the oil production and increase the oil recovery. So in 2006, there was a competition, and the winners of that competition were actually Dr. Håvard Åkra and Dr. Vidar Mathisen, 2 of our founders of Inflow Control when they worked at Statoil. And it was the first generation Aicd, based on Bernoulli's behavior and equation. It's a floating disk, much like an airplane, which was a much better improvement to the passive Aicds. And it allowed you to get up to 20–30% improved capabilities of managing unwanted gas. There were limitations, but it was a huge improvement. And from 2006 until 2012, that was the best autonomous device on the market. When Inflow Control invented the Aicv, the goal was to create enough closure force. So for any mechanical engineers or completion engineers on the call, you'll be able to relate that to shut off an unwanted zone, much like a safety valve, or much like a wellhead, you need to have closure force, mechanical or hydraulic. Our technology actually has the ability to hydraulically choke or close off the main section of the valve. And that's the big difference from other technologies, is that our valve is like a hybrid between a hydraulically controlled smart valve and then a passive inflow control device. So from 2013 to 2022, we now have almost 200 wells installed around the world. We have the largest track record in the Middle East, or the GCC, of autonomous flow control technology installed. And in 2015, which is analogous or comparable to your reservoirs in Iraq, in Saudi Aramco, we to date are still the only technology company that passed, to our knowledge, the autonomous inflow control TTR process, which is very stringent. It's called the Technology Trial Readiness Program. And we're quite proud of that because Aramco has a very structured process to approve technology. And the benefit for the reservoirs in Iraq is that they're almost very similar. Very light oil, we call it ultralight oil. The mobility between the oil and the water and the gas is high, but the difference in the fluid viscosity is not much. So the historical devices have not been able to help your reservoirs. We have something that we've been running for 6.5 years off the shelf that actually can handle all of the ultralight oil. Next slide, please. So the improvement over the past 30 years comes down to technology. There's nothing but technology and science behind how the technology behaves. So this is a graph showing the performance. On the x-axis, you can see the flow rate in liters per hour. And on the vertical axis, you can see differential pressure in bar. So the dotted line is showing single phase testing in a flow loop. And this is reference to paper OTC 28860, which you can find and review on your own, or we can help send it to One Petro for you. First, I'll look at this. The dashed gas AICV line is showing what happens at differential pressure for single phase gas through an Aicd, which is essentially just a hole. It doesn't have any change in its flow area. You could have a cylindrical, helical path. You could have a hole, a nozzle. The point is, it's just a choke, but that choke doesn't have the ability to change its flow area. So it is static. So you have to live with whatever diameter choke is. So when you have gas, that choke, or the Aicd, is going to flow a ton of gas as it comes through. So the example is when you have a gas breakthrough, it will flow a huge volume of gas. And what does that mean? That means you leave behind all the oil. Now, if you look at the solid red line on the left, you can see it is nearly fully closed. That is what happens when you design the AICV to shut off aggressively the gas. So in the middle, you can see there's a dashed green, a solid green line, and a dashed blue line. That is indicating the oil and the water in the dashed lines for the Aicds. And the solid green is indicating the oil contribution from the AICV. So the short summary, 30-year-old technology for the passive Aicds was good at deferring the breakthrough, but now there's a technology that can change its flow area without any intervention and no control lines to surface. So it will stay open for the oil, which is our AICV, stands for Autonomous Inflow Control Valve. But as your GVF, or gas volume factor, or water cut increases, whatever the multi-phase flow is, our valves will start to self-regulate depending on the composition at the reservoir level. So when there's oil, the valve stays open. As the water and the gas increase in a certain zone, those valves will behave accordingly and begin to choke the unwanted phases until it's a very high gas proportion or very high water proportion. And then the main section of the valve will close. Next slide, please. So in this cartoon, we're going to look at the challenges with horizontal wells, because when you drill horizontal wells, you have a lot of benefits. You maximize the reservoir contact. It minimizes the cost and how many wells you have to drill to get that reservoir contact. But when you have non-uniform drainage, you then create this gas and water breakthrough, notably inside fractured carbonate reservoirs. You also have this friction inside the liner, the completion string, and this variability in the fractures or the perm is going to cause different flow of the water and the gas versus the oil. So when you have these issues, it then causes, unequal flow, where you want to distribute your drawdown and your flow. But when you do have gas and water, which is a fundamental reality of oil and gas reservoir management, you have to do something about it. So instead of doing an intervention and trying to figure out where the gas comes from, where the water comes from, what you can do is create compartments, as you see here with the swell packers, these little black rubber pieces. And by introducing the autonomous inflow control valves, the valves manage your uncertainty. As the water cut and the gas cut increases on certain zones that are isolated by packers, you create the compartments, and then you get to choke off the water and the gas zones. But the zones that have the oil in them are enabled to be produced. So if you go to the next slide. So you can forward all the text, Safe, please. So when we're looking at this on a reservoir drawdown perspective, as you can see here in the different pictures, the valves you can see that are in the oil section. If I start from left to right, you can see that the little gauge, just to give you the visual, are open. Now, if you look at the center one, you can see the valve indicating it's closed. But what I want you to do is look above that valve at the bar chart. Now, what is occurring here is that you are having the reservoir delta P, it's across the valve. So by having the valve take the drawdown, the delta P, pardon me, you are then enabling the zones that have a lot of oil to then create more reservoir drawdown. Because by increasing the drawdown on your well, typically, if you increase the drawdown on a well when you had a water breakthrough occurring, you would then have more water produced. So one prescription that many people do that don't have control in their wellbore downhole, if you start producing water, you may turn down the drawdown. We actually want you to do the opposite. By introducing packers into your completion, you then can isolate the water, and you can see the different sections of the well where you can introduce more drawdown on the reservoir. So introduce more drawdown on the oil bearing zones, but the sections of the well that have high water cut, the valve will take care of that, and it will start to choke aggressively. As the higher water cut or gas comes through, the valve will start to self-regulate and choke. And historically, you didn't have a technology that could go down to ultralight oil. But now, for the last several years, we have a technology that's been proven down to 0.25 centipoise, which we understand covers all the reservoirs in Iraq. And we have that technology to be able to do this now off the shelf. Sorry. I apologize, I'm trying to control this. So the technology, the valve is very unintrusive. So that means is that it can be introduced into almost every type of completion. We'll introduce it with a wire wrap screen or a premium screen, depending on if it's a sandstone reservoir. If you have a carbonate reservoir, we'll just put a simple filter. So there'll be no additional pressure drop across the sand control. The valves will be introduced either in 1, 2, or 4 per each tubing joint, depending on the flow rate that we have. Because the valves are self-regulating, they need to have enough closure force, which we're going to show you. And the valves are full bore ID, which means that you can go in and do any interventions. But we designed the valves for your reservoir. So this is an important point, is that if you have a reservoir with light oil that's say 1 centipoise, and you want to control water very aggressively, we will design the valve based on your knowledge of your reservoir, your operating principles, and what you want to achieve. If you have a well that's even lighter oil, say down to 0.5 centipoise, and it's a fractured carbonate, and you want to control the gas, we will then design the valve accordingly, because we can change the parameters of the valve to be more suitable for your reservoir. And we have dozens of different valves that we would design and apply, all been tested and proven. So to give you an overview, just to visualize, you can see on the right-hand side, it's showing a small swell packer. You have zonal isolation. That's important because the valves are very good at what they do, which is stay open for the oil. but choke or close off for the high water cut and high gas when it flows in. So to be successful on a reservoir level, we need to create that zonal compartmentalization with packers, be it mechanical or swellable. The reservoir fluids will flow through the screen, or if it's in a carbonate well, the filter, and then it will flow underneath the drainage area into the housing, into the AICVs, and up to surface. So we're going to try to play this video to explain how the physics operate within the AICVs. If we have any challenges, can you please just let us know, and then we will send you a link so everyone can see after the video. Can someone let me know if they can see the video working?
Yes.
Okay. So I'm going to pause here now. So this is showing where the AICV is located under the protective housing. So it's installed inside your base pipe or tubing. We have the filter either for sandstone or carbonate applications. The filter keeps the debris out, or the sand or the fines, to whatever point is designed for. The main flow area does all the benefits of passive chokes or passive Aicds, where you can see here inside the main section of P1, where P1 is located, that's your first choke. Then you can see the bypass line on the right, which is called the laminar flow element, which takes roughly 3% of whatever multi-phase flow that portion of your reservoir is flowing. So the valves will remain open because the fluid flow that goes through the laminar flow element on the right is going to control the P2 force, which pushes upwards on the main flow area. Now, depending on the composition of oil, water, and gas, you will have a certain pressure drop through the laminar flow element. That pressure drop then combined with the TFE, which is the outlet in the center, will create an upwards closure force. So P2, when it becomes stronger than P1, begins to push up and close the main flow area. As oil has different properties than gas and water, you will have a higher pressure drop. And you can see in the cartoon that water is flowing through the LFE, and it's all based on forces. Sorry. My apologies. I'm going to try and find this here. There we go. So I'm going to pause here and just talk about the forces, because this is a very important part. So as I just rewinded slightly, you can see that as the water flows through, it creates an upward closure force underneath the disc, which creates a hydraulic piston effect. So if you can see on the chart on the vertical axis, you can see P1 to P3. P1 is the choke on the main section of the flow as you're flowing in, just like a passive Aicd. Now P2 is the force generated through the laminar flow element, and that pushes the disc closed. And the disc is fully reversible. So as you increase your oil proportion, or if there's any reservoir dynamics that change, the disc will relax itself. And you have sometimes slug flow in the reservoir, so you don't want something that closes on or off on its own. And it's a key point to tell you about that the disc is dynamic. So if you only have a small amount of water, you'll have a small amount of choking force. And again, use that word force, because this creates hydraulic closure force. But when you have a high proportion of the water cut, the amount of choking force becomes higher. And what that means on the reservoir level, like the earlier cartoons, you create choking effects where the water and gas are greatest. And then you have the valves that remain open on the sections where the oil is saturated more. So you improve your net oil contribution, you improve your recovery, you reduce your issues with lifting the gas and the water. And if it's a water issue you have, you can reduce potentially the pump size, which is electricity cost. And the electricity costs are going through the roof all over the world. So why pump the water when it does a disservice to the oil production? And we understand you may need some water for brownfield production. And that's fine. We can design the valve to be less aggressive. but you don't need to produce zones that are 100% water cut. And we've proven this with many operators by improving the amount of net oil we can increase from their reservoir. Typically where they thought that they needed to produce all of these zones that were high in water cut, it's not correct. What I wanted to show about this around the world is over 65% of the reservoirs in the world are light oil. So what does that mean? Light oil, less than 3 centipoise. And if you look here in the GCC, the majority of the reservoirs are very light, which creates great final product, but it creates a massive challenge to try to manage the unwanted water and gas at the reservoir. And this is a key point to highlight, because as we understand from the reservoirs in your area, we have a solution for almost all of the reservoirs off the shelf from the work that we've been doing within Saudi Arabia, within Oman, and within the UAE. And the challenge was that you didn't have enough difference between the viscosity contrast and the density impacts for technology that was proven. So our goal is, again, to maximize the oil recovery and minimize the unwanted phases. So if Mahmoud, if you're on, I can hand this over to you if I go through the slide. What this chart is showing you here, our valves can go down to 0.25 centipoise for gas shutoff. So what that means is that if you have oil in your reservoir and it's at zero down really light, 0.25, that's almost condensate. Our valve is something off the shelf that you can order today to manage your unwanted gas, high GOR. For water control, you can see on the spectrum from left to right, we go from 0.1 up to 1. This is really difficult to do. We don't even talk above 1, everything works, no problem. When you look down at the water choking, this is game changing. The last few years that we developed this, there's nothing on the market that has been proven to handle this light of an oil and water contrast. So we can choke the water down around 0.5, 0.6 by 20-25%, depending on the properties. We need to look at your reservoir and fluid properties to give you a definitive answer on what we can or cannot do. Because the valve works great in most reservoirs, but not everyone. So we have to review that and understand if it is a good solution or not. But we can get down to 0.5, 0.6 for choking versus the oil, which has never been done before. But when we define the water shutoff, when our main flow can self-regulate and shut itself off, that's around 0.8, 0.9 and onwards, because density, salinity of your water play a big impact on that. So short takeaway on this is we have a gas shutoff Aicb for nearly every reservoir in the world, and for water choking and water control, we have an Aicb off the shelf now for ultralight oil, and for light and medium, it's off the shelf proven as well. So without further ado, I'd like to introduce our Reservoir Engineering Manager, Mr. Mahmoud Abdel Fattah. I say, is Mahmoud there?
I don't see him, Brent.
Okay. No, I know we had technical challenges with a few of our machines before, so I'm going to continue then. What this is showing you here, this is one of our most advanced Aicb technologies. And there's nothing like this in the world, and we're very proud of it. And to be humble, I have to calm down, and I apologize, but we're excited because this can change 65–70% of the reservoirs in the GCC today. What this is showing you on the x-axis is the fluid rate, or the total flow in liters per hour. Testing is done in our facilities in Norway, and the differential pressure on the vertical axis. So when you look at this, the green addition squares, the green tags, this is an oil used in our lab to test for 1 centipoise oil. So that's showing that each dot, if you can plot it from the vertical axis and then go across to the right on the x-axis, it's showing you at single phase oil what flow rate you get per valve at 100% oil. So if you take it from, say, 15 bar and you go across and you see 100% oil, that's roughly going to give you almost 600 liters per hour of oil. Now, if you have 100% water, it's going to be able to choke that light oil reservoir water down to roughly 150. This is almost 5 times difference. 5 times difference of control of the unwanted water to the oil. So the multi-phase flow will be somewhere in between that ratio. And depending on the proportion of gas and water to the oil, you will have it in there, because not every well is going to be just two-phased. Typically, we always see a lot of multi-phase wells, but every reservoir is different, and you know your reservoir is better than us. But this is game changing. There's nothing on the market that's been done like this. And this is something today you could order. Once we did a simulation review with our talented reservoir engineering team, this is a tool that you could order off the shelf. So what this means is you'll be able to produce roughly 4.5, 5.5 times more oil per water, depending on that composition. So if you have a very high water cut in a certain portion of your wells, the valve will manage that. You will not have to spend the money on running a log.
Please go ahead. Sorry for that.
You will not have to spend a lot of money, because what happens when you have a water breakthrough or gas breakthrough event, the first thing is understanding where is the challenge in your reservoir. So finding the solution is the first thing. Second thing is then figuring out a remedial approach on what you're going to do to fix it. So in this case, though, you can imagine the valves manage this uncertainty, because the reservoir dynamic models are based on models and assumptions, but Mother Nature throws curveballs. And when she does, we have to be prepared to be able to actually manage that. So this manages your wells accordingly, and you don't have to do any more interventions to then help take care of this unwanted water and gas. So this is great. This is an overview of the data. We have nearly 24 publications, several with other oil companies, which we will share at the end of this, or Safe can share with you. We like to show about where the real world results. So I went through a lot of the overview, a bit of the marketing slides to try to get the message across, because our valve will stay open for the oil and it starts to choke and close at the higher water cut in the gas. But we want to see where this has been done. So this is case study number 1, and it's a reference to a publication, IPTC 20195. Now, what I want you to take note is this is like a reservoir in Iraq. This is a reservoir in Saudi Arabia, very, very similar to the reservoirs in Iraq, right next door. This well was producing for over 10 years, between 3,000 and 4,000 barrels a day. At the beginning, it was producing even more, but that's confidential. So this well is over 10 years old. It was doing fantastic. The operator had a huge amount of oil produced from this one well, and it got older, and guess what? The gas found its way in through the fractured carbonate network. So due to the high GOR in the well, and this asset ranges ultralight oil from 0.45 up to 0.65, so it's ultralight oil, and they had to shut the well in. So when you shut the well in, you're not making any money. You're not producing any hydrocarbons or any oil specifically, and they couldn't handle the gas. So after many years of reviewing options, they found this technology called the Autonomous Inflow Control Valve, the AICVs. They did a lot of review on how to apply the valves, and they determined that for their application was to retrofit the well, so it's an existing barefoot completion, with a combination of AICVs and hydraulic and swell packers to then restart the well. So how we approach this is we have one of the largest teams in the world inside any technical vendor service company for reservoir engineering and subsurface design. So we have 3 offices in the Middle East, here in Abu Dhabi, where I'm located, in Saudi Arabia, in Muscat, in Oman. Then we have offices, 3 in Europe, 2 in Norway, 1 in the UK, office in Canada, office in Houston, and an office in Bogota. Can we produce the AICV in vertical wells? Yes, we have a good case study on vertical wells. I see Sarah's question. I'll come to that question at the end, Sarah. So yes, the valves can operate in vertical wells. We have a good case study that I'll come to in a moment. Back to this case study 1, when we take the technical team, we'll give you an input data sheet to try and fill in the understanding information points that we need from you to understand your reservoir better. The perm porosity logs, LWD data, completion data, production history, and reservoir fluids. Then we will review all of this information and come back with a preliminary simulation. And typically this is an iterative process. As I mentioned at the beginning, you know your assets better than anyone. So we need to learn from you how your asset behaves, and then we can propose a simulation. So this simulation here happened after many, many iterations. So you can see the perm log on the top, and then you can see the contrast along with the saturation in the second section, you can see there's some significant gas saturation there between 7,000 and 7,100. You can see a significant water section around 7,800. And on the bottom chart, you can see this is the completion, which is showing in the red squares, swell packers or mechanical packers, and the blue little squares with the black dots are indicating our AICVs, and these are dual AICVs. So the operator determined we're going to compartmentalize their completion with 10 zones. So we had packers to make 10 compartments, and you can see from 10 on the left up to number 1, there's sometimes 2 or 3 joints in each compartment because we need to have enough flow rate. And then we have dual AICVs because this is a larger flow rate well. So what you see now is the results. And this is backed up with publication with the operator. On the bottom, you can see pre-AICV, there's a significant amount of gas. And you can see that there is an open hole completion, barefoot, fractured carbonate. You can look at the top of the pre-AICV on the bottom section of the log, the PLT or flow scanning imagery before it was done. What you should notice is the significant amount of oil saturation in the lower half of the well. And our duty to produce these oil reservoirs is to maximize your oil recovery. So you had stranded assets, stranded oil in that reservoir. Now you can see on the top section, after we installed the AICVs and created the compartments with the packers, it managed the free gas. There was still some solution GOR, but it opened up that lower section of the well by the valves enabling to manage the high GOR zones. And the valves opened up that trapped hydrocarbon there on the lower section. So on the right-hand side, you can see these graphs, which are more explained better in detail on the IPTC paper. But 90% reduction of the gas and 5 times more oil from that lower section of the well. This was a well over 10 years old, everyone. It's the opportunity to go into old wells, not just the new ones, is vast. You can look and review all of these old wells that you previously couldn't produce because they had too much gas, too much water, or both. And this is what's exciting because it's a really low economic threshold to come over. So that's case study 1. And as I mentioned, you can see the GOR 90% reduction, 5 years stable oil production. The payback was less than a month. At $75 oil, the amount of oil produced from that is over $300 million. And these are estimated figures because this is confidential information. So we took a $75 average price on the production over time. This is amazing, absolutely amazing. So I see a question came in. What max rate can you obtain through an AICV? The AICV flow rates can be designed for various rates, and it depends on how light, how heavy the oil is. So since the valves need to be able to self-regulate it based on a force equation, which means is that you need to have enough force pushing up from below to overcome the force that's coming in the main section of the valve. So if you make the valve too large, the force equation becomes impossible because you need so much force underneath. So the simple workaround that we have to handle higher flow rate wells is you put 2 AICVs on each tubing joint, or you put 4. And we have many wells where we have very high flow rate wells. We're in a well that's over 10,000 barrels a day. So the design for the high flow rate wells is not an issue at all. But it's not a linear question for each valve because it depends. The valve behaves differently for different oil properties. The question from Kareem, can we use it in all wells? Majority of the wells we can. What we have to look at first is, can we help you with your reservoir properties? It depends on the reservoir properties first. So Hussein, actually, this is probably one of the most cost-effective alternatives to a smart well completion. The question was asked, can we use this with a smart well completion? The short answer, can I open my stuff? Sure, please. Ali, go ahead.
Okay, thank you. I'm Ali Yusur from Basra University in Iraq. of the last year of oil and gas engineering. Firstly, I would like to thank Dr. Wafiq and all the instructors in this session for this valuable information about Aicb. In fact, I had two questions about that. Firstly, what are the disadvantages of the Aicb in addition to the high cost? Secondly, how can we use it in gas reservoir when we are dealing with water and gas together at the breakthrough, especially if the device is viscosity sensitive? And as you know, water and gas has low viscosity. So how can the device to prevent water and allow gas to produce at the same time? Thank you again.
Good. Thank you. I'll try to. So I'll answer your last question first. So our AICVs are designed currently for oil reservoirs. So we have in our research and development department, we have a gas AICV which is meant for gas reservoirs, which is not yet commercial. So again, so this discussion for everyone on here to clarify, this is an autonomous valve to be used in oil reservoirs to produce oil from oil reservoirs, but to choke or close gas and water from oil reservoirs. We don't yet have a valve for gas reservoirs to produce gas. When the next, to the next question on the high cost or of the valves alternatives, the payback period for our technology is really low. It's much cheaper than a smart well, dramatically cheaper. The payback period for most of our wells, because we help produce so much more oil, it's anywhere from 3 weeks up to 3.5 months. So our payback period is probably one of the best investments that you can do for retrofitting a well. But again, we won't recommend implementing our technology if it can't help increase your profitability. Full stop. I think the economics is probably an exciting discussion. As you see in the last application, that operator paid back the entire drilling and completion program in less than 1 month. That's the rig, the downtime, the PLT, and the AICV completion. That's phenomenal. There's no other technology where you can have a payback that fast, unless of course you're drilling a new well. But for retrofitting old wells, vertical or horizontal, the technology has a massive amount of profitability return on investment for the oil companies. And this is what gets really exciting for us is we will recommend the technology application only if it can help you. We say no to probably 25–30% of the applications simply because it might not be the right fit or it might not help the operators. And we do all of our simulation and modeling free of charge. We have a couple dozen subsurface reservoir engineering personnel, men and women all over the world. They're fantastic. And we do this free of charge because you shouldn't be paying for something to find out if it's going to work for you or not. That should be something that the companies invest in, and we believe in that. On the other questions, can it be run in horizontal wells? Yes. Majority of our wells have been horizontal. We have many that are deviated, and we have some that are vertical. There was a question, Safe, I don't know if we have the other case study for the vertical well. If we do, could you jump to it? If we don't, we can share it with the team. But as we talk about this, the biggest screening discussion for vertical wells is to make sure that we have enough reservoir depth. And when I say that is that if you have a very shallow reservoir zone, since we need to run the AICB with some kind of packers, thank you very much. As you can see here, this well, is long enough in terms of the perforation sections that we can space out the number of joints with the packers to isolate the different reservoirs. So this case example is a vertical well where it had 2 different varieties of reservoirs, so 2 different layers producing. Now with these 2 different layers in this reservoir, they had different pressures. So what happens when you have different pressures that are supported with water injector nearby? You're going to have one of the zones dominate the flow. So one key challenge that we had faced is the operator wanted to manage the high flow zone that was very connected to the nearby injector. And we did that successfully. And that allows the injection of the water, instead of just recycling all of this water, it allowed the valves manage that high connective zone. And then that allowed us to then open up the other top zone and manage that unwanted gas that was coming through. So this is to stabilize the flow So when you have high gas or water, the valves manage the uncertainty. They've made massive profits on these wells, and this is retrofitting applications. Sorry, there was a question, I didn't catch it, that came up. I think we could take the questions now. We went through the technical components, and I see we've got 10 minutes left. If our hosts recommend it's okay to have the questions now, would you like to go into Q&A?
I prefer to finish the presentation, then we will start the QA session.
Understood, thank you. Okay, so let's go back to the presentation, Saif, and we'll just finish this off and then get to the Q&A. So this is again a summary to try and tackle it. It's all about the profitability, and all the profitability is going to be achieved by managing your reservoir. So the technology, when you can apply it, as this is showing here, this is a case example where we had 3 wells, and this is an extrapolated value over 3 wells. So these wells were all retrofits, which means they were already existing. So the operator already had the infrastructure in place for the pipelines, the wellhead, but they couldn't produce the wells because they were stuck with a very high water cut. So what we did, retrofit with the AICVs, and you can see the increased oil. Now this is at $70 oil. We're not trying to blow the numbers up at 100. You can do the math, $30 more per barrel. The incremental profit, and that's the goal of an oil company, is to increase your production and maximize your recovery of oil at the lowest cost as fast as possible. But the additional savings by not producing the water was they got to reduce the cost and energy of pumping it, got to reduce the cost and energy to handle the water on top side, and all the energy needed to re-inject the wells. Also remember, on a reservoir level, when you're having so much water being produced, the water is injected for depletion and pressure support. So when you have your voidage support, and then you need the pressure for sweep efficiency, if you're producing all this water through, that's not helping you sweep out the oil as efficiently as possible. So the zones that are either highly connective or very high already in the water cut, water saturation, you want to manage those zones, and that's going to enable better pressure in the reservoir, less injection, more net oil. Next slide, please. Again, we talked at the beginning, we're nearly 200 wells. We're almost doing a well a week now. We've got nearly 24 publications. It says 16 here, but we have a few more now that we can share. We have a track record in the Middle East that is very analogous to your reservoirs. So we have experience in very similar reservoirs. We think we have a valve for almost every reservoir from what we know now. We could be wrong. We need to understand your reservoir before we make any assumptions. We have 3 different locations in the Middle East that we can actually manufacture. So we do all our valves in Norway, but we have 3 different options. So our ability to service you locally fast is very, very high. We have an ability out of Saudi, out of Oman, and out of here in the UAE. So we have a very fast response rate. And we have 3 offices here in the GCC to service. This technical, these data, we try to share how the reservoirs work. So we have a massive amount of information on YouTube. If you have time, grab a tea or a coffee and watch some of these videos. A lot of the ones on the left from video 1 to 6 are fundamental reservoir engineering discussions from our CEO and co-founder, Dr. Vidar Mathisen. He's one of the subject matter experts around the world in this topic. And then from video 7 to 12, we get into more details about how different technologies can be used and the physics behind them on how they can help produce more oil. So we actually take a different approach. Instead of being secretive, we want to share with everyone about how we try to tackle problems. And if we can help, it's fantastic because it's going to make your business a lot more net oil. Next slide, please. So I'd like to thank the Basra SB section, AGRC, for allowing us your precious time. We know everyone's very busy within business and within studies. So myself, Brent Bruff, I'd like to thank you. Also with my colleagues Saif and Mahmoud. We really appreciate your time and look forward to taking any questions you have. Thank you.
Thank you, Brent, for your nice presentation and informative talk actually about this interesting topics. So now we can start the QA session. So anyone has a question, may write it on the chat box or ask the speakers directly, as we prefer. So Brent, can you return back to the chat box to see if there are some questions left that have not been answered yet?
Can you hear me?
I just hear you.
Okay, thank you.
So-
Saif, do you want to share the chat box on your screen?
You are co-host. I think you will be able to see whatever there.
Ah, okay. There we go. Okay, the questions. There we go. I have the questions pulled up. Thanks. Sorry, I haven't used Zoom so often. I apologize. I apologize if I talked at too fast a speed. If there's further questions though that we have after this, please we can share them with Saif or the team, and we can help answer this. So, first question, I guess, can we use Aicb to control the pressure drop in vertical wells that have 2 producing units? Yes, and we have experience with that. So short answer is yes. We get information from you on your wellbore. We can go through that. In what types of existing wells can it be utilized? As long as you have a well that we can enter safely, and when I mean safely, if you don't have big obtrusions or you don't have a collapsed wellbore, and then you have a long enough reservoir section, be it vertical or deviated, then those would be good candidates. So the first questions we'd ask is, the length of the well, the reservoir properties, typical flow rate history. And one key thing is that sometimes a lot of operators want to use this technology in wells when they've depleted almost all the oil. So the valves are very good at what they do, but we need to make sure that there's still enough commercial oil left in the reservoir. Next question, max rate obtained through the Aicvs. Does rocking open wells adverse effects in Aicp? And no, so like for open hole completions or cased and perf retrofit, we can apply the valves in almost any type of completion. So that's not an issue. It's just a matter of making sure we have enough space to get the completion into. And we do retrofit, for example, 2 3/8 or 2 7/8 tubing into existing 4.5-inch completions. So we have experience with that as well. But when we review if the valves are going to be able to help your reservoir, that's the first step to try and review if it's going to be suitable or not. Next question. If we decide to perform a stimulation after 2 years or more, can we do that to pump to dissolve asphaltene and paraffins? That's a great question. So we have our inflow control valves. We also can couple it with an injection module. So if you want that ability to inject, because the valve on its own has a very small reverse flow volume, because it's very good at controlling production, but it's not meant to be an injection tool. And there's a lot of technologies that people say, I want to inject and produce through it. And that's good, but you need to understand the limitations as a production device. If you can inject the same volume through it, you're going to produce the gas and water through that device as well. So we take a very different approach that we designed the Aicvs to manage your production, open for oil, closed for high water cut and high gas cut, and choke in between. And then we add an injection module, which is very small, that will go in the housing beside the Aicv, which you can then inject through. So if you do have to perform some stimulation in the future, you can just add the injection module. So that's similar to what we do with ADNOC. Can we use the technology in horizontal wells? Yes, absolutely. Next question was Chrome 825, special handling on the surface. So we will design the valves according to the fluids that the valves are going to be exposed to. So if you're going to have hydrochloric treatments, we'll design the valves accordingly. And this is all part of our review process. The valves are made out of tungsten and stainless. And yeah, we do use high quality metal. But because you don't want to intervene, we want you to run this completion in and leave it. Let that well produce for years and years. So you don't need to do any intervention. The estimated cost to install the technology in a vertical well of 12,000 foot depth. To answer that better, we need to know flow rates of the well, which would mean how many valves we're going to design. if we're going to run acid or not, if there's CO2 or H2S, all of these factors, and then we can give you a quick answer. But as I mentioned, the payback for our technology is very fast. Typical 3 weeks to 3 months payback, very fast. The next question, did the AICDs operate only on fluid viscosity as written as density? So ours is an autonomous valve. You can think of an automatic inflow control valve. So why we call it a valve is we have closure force. So this is a question to Sajid's question. So our valve also works on density because the laminar flow element, there will be a density portion, and we can share our SPE papers, which go through the calculations on how you can actually model this. If any of you have net tool modeling, we can give you our coefficients so that you could actually do your own modeling in parallel with us, so you could run your own simulations. We do that with quite a lot of operators around the world. If you have any dynamic modeling software from T-Navigator or Eclipse, you can give us the files and we can look at that information as well to give you a simulation. Yeah. So density does play a role in our technology, is a short answer. There's 2 more questions come up. If one valve breaks down, how can we figure it out? So we have not been able to destroy a valve yet that we know about. So we designed the valve with a very high degree of integrity. So the valves don't leave Norway unless they pass our stringent multi-phase factory acceptance testing. So that's one. Again, then when we ship the valves to different parts of the world, they're put inside a very protective housing. So there's nothing that can damage it unless you have a severe well issue, but that housing is very strong to protect the valve. So after we install that into the screen around the world, if it's in the Middle East, if it's in South America, if it's in Canada, there's then another set of testing done to make sure that there's full pressure integrity of the valve. So where's the Aicb be installed? Is that the options in your question? Do you mean where's the valve been? If the question, so we've installed in several countries around the world. The valve would be installed on a tubing string, and that tubing string would then have some kind of screen filter, and the Aicb itself would be protected in a metal housing. So there's nothing that's going to be able to damage the valve from outside. And you don't need people on the rig to run this. There could be someone there to supervise if needed, but we would be able to do all of the operational support, but it doesn't add extra people on the rig. You don't have any control lines. You don't need to get any special wellhead to feed through any hydraulic lines. There's no connections to surface. So you don't slow down your operations on the rig. What kind of maintenance the valve needs? The valve's dynamic, so it's always going to be moving. So I know one question comes up from people about if scale happens. You can inject at a slow rate backwards through the valve at a very small volume certain chemicals, and we just need to know what chemicals they are to help clean the tool if you have asphaltene or paraffin deposition, for example.
Okay, so does anybody else have a question that he wants to ask the speaker directly? Okay, so I have 1 or 2 questions. Do you hear me?
Yes, please.
Okay, so are there any limitations of the AICD to handle the amount of water cut, especially in the reservoirs that are surrounded with infinite active aquifer, like the southern Iraqi oil field?
So to look at this, if water is everywhere and there's no oil remaining, then I think it's a challenge, right? As I mentioned, if there's still, I'm going to go to slide 23 if it's not clicking on here safe. So as you can see here, you're looking at the saturation log. If you can see this from left to right around 6,900 to 8,300 on the well, you can see there's significant amount of oil saturation. So in your situation, if I understand the challenge of the reservoirs, that water is everywhere or water comes from everywhere? I just
no, actually, some of the southern Iraqi oil field, the sandstone reservoir surrounded by infinite active aquifer, that the aquifer is located either at the bottom of the reservoir or at edge edge water drives.
Yeah.
So we have some reservoirs that the water cut reaches to 60, 70, or sometimes 80% in vertical wells. So my questions was regarding the limitation of this new technique to handle that amount of water.
Yeah. So first, we would just have to look at the reservoir properties to understand where the limitations are. The valve, where it can be applied, will work very well, but we'll review if it can apply or not. Now, to understand this, I think we'll get as much information from you. And then the spacing of the vertical wells is going to be important to understand where the wells are drilled in relation to those aquifers are going to be very important. Because if they're drilled in a large portion of the water, but there's still enough oil saturation on different parts of the reservoir, the valves might be able to help. But we need to understand it if the water is coming in all parts of the zone in the sandstone, or if there's going to be predominant zones which have that 60, 70% water cut. This case example here, it's not vertical, but it's very similar in terms of it's a very old reservoir. It's much heavier. The water is bypassing the oil frequently, and they typically have up to 95% within the first 12 to 18 months. What they had a challenge is that water was bypassing all the oil, so they thought they historically would have to produce all this water, but they were convinced of our technology, and they applied the technology to manage these very high water cut zones. But they said they didn't want to be so aggressive. They still wanted to produce some of the water because it's a multi-phase flow. It's not just water and oil, it's both. So the zones that have a very high water cut section that's when the valve becomes more aggressive, and we can design that. So in your reservoir, if you have water coming from every part of the well, then we can look at how we can design the valves to be maybe a little less aggressive until it's a very high water cut, such as 75 to 95%. So that we would tailor after we get the information, but we would just need to get a bit more information to give you a more quantifiable answer.
Okay, great. Before I ask you the second question, there is one more question at the chat box from Hassan and Abid.
Hassan.
If you see it.
Yeah, Hassan, they could range. The valves could be, if they're very simple material, depends, could be 16, 20,000, it could be 30,000, 35,000. It depends on the metal. Like the metal cost these days, if you're going to run, say you have high CO2 and H2S, to do the exotic metal, the metal prices are very expensive now. So it can range that far in between the valves because, like, for example, we have some projects where it's very corrosive. So we have to pick very exotic metal, and that metal price is very expensive right now. So it all depends. If you can send me an email or safe, and we can do that very fast. We can give you a rough estimate. Yeah. So what determines the valve cost is the number of valves per well that we need, and then it's the metallurgy. It's pretty straightforward. Yeah. And then obviously, if you have different sand control needs for the sandstone reservoirs, it might be a bit different, but it's predominantly the number of valves and the metallurgy that really impact these days, because the costs of the metal have skyrocketed. Yeah, but again, I have to stress the payback and profitability that these valves can generate if they can work in your wells is phenomenal. It's absolutely phenomenal. This case study 3 that I'm going to click through on slide 36, you'll get this slide pack from SAFE. If you go down to slide 36, these are marginal wells that were run in over 2 years. This was the value return in the operator in over 2 years. They increased the net oil. This is above their conventional wells, but they reduced the energy costs required to lift because of the reduction of the water, and the $10 million increase in revenue. So yeah, it was we're pretty excited about this, but if we look at your applications and we can't help, we'll be very honest right away. But we all do this for free at the beginning to the front end. And yeah, if you have some interest, we would love to take a look at your data and see if we can or cannot help you.
Okay, thank you. So I have just one more question. We know that the inflow control device is usually installed in the wells in primary and secondary recovery. So I was wondering about the feasibility of installing them in wells in the reservoirs under tertiary recovery, specifically in the gas injection. Some process of the gas injection, we inject gas at the top of the reservoir, then oil and water drain down to the bottom of the reservoir. Series of horizontal wells installed above the oil water contact. So we get fast production, then the reservoir tends to have water cresting. So we will have high water cut. And sometimes when we consider immiscible gas injection, we will suffer from fast gas breakthrough. So we will have gas breakthrough and water breakthrough. So have you like tested this AIDC to handle this tremendous amount of gas and water in tertiary recovery, specifically in miscible gas injection?
That's a good question. I would have to go look at our track record if we've had an exact example on the tertiary recovery to answer you accurately. So I don't have an accurate answer right now. But if I just maybe break it down to the fundamentals, you have a high gas breakthrough and high water breakthrough issue, correct?
Yeah.
That's the whole purpose of the valves. It won't matter how high the rate is. And one question, no one's asked the question about erosion. There's no erosion issues when you stop the high velocity. And usually you have erosion when water brings fines and you have a very high velocity. But because the valve can aggressively close a very high gas breakthrough or water breakthrough, it gently chokes until that water cut increases. So you stop that high velocity channel. And when you stop high velocity flow with the fines and the water breakthrough, you kill the erosion concern. So that's one thing. But back to your question, if it's gas and water control, that's exactly what the valve does. The most important thing is to make sure that you can segment the wellbore in the tertiary recovery that we install it in, that there's enough compartmentalization, because making these compartments with the packer, it's not so complicated, but these packers need to work, because if the packers don't isolate, the valves will do what they're designed to. So if a packer leaks, the valves will see gas, and the valve will do what it's designed to, which is choke. So when we do the design, we help support all aspects of that design. So if you give us the information on the tertiary, we can look at it and see if we can or cannot help. And then we will give a recommendation on how to compartmentalize the well. But in short, if you have gas and water breakthrough that's stopping you from recovering the oil, the short answer would be yes. But let me get back to you on more quantifiable answer, please.
Okay, thank you. Actually, at the OTC, I presented a paper to solve this problem in different way. To use the gas downhole water sink assisted gravity drainage process that we install horizontal wells underneath the oil water contact, exactly underneath the oil producers, the horizontal oil producers. We will have horizontal water producers to produce or to sink water from the water zone in order to reduce the tendency of the reservoir of water cresting and reduce the water cut. Also, we used immiscible gas injection, not miscible, so we had lower gas breakthrough than the miscible case. So the new process that we have developed at the Basra Oil Company called gas downhole water sink assisted gravity drainage process. I can share with you the OTC paper number later.
That would be really good, yeah. So there's many more, there's much more smarter individuals in our company that I would get in talking to you, and I understand my limitations, and this discussion I would need to bring to our heads of reservoir to have a proper discussion with you on that. But that would be exciting. It sounds like a fascinating topic.
Okay, so thank you for your nice presentation and interesting information about this this technology, and thanks for your colleague Saif, and thanks to all who participated in this webinar. Thank you all.
Thank you, Dr. Wathik.
Thank you.
Thank you everyone for your time. Have a great weekend.
Okay, you too. We will share the presentation to the participant through Telegram or another social media later. Thank you. Have a good day.
Thank you.